All right, good evening. All right, does it work? No, it doesn't. Need to tune that up a little. Test. It's better. All right, you can all hear me? Wonderful. So, as usual, please take your seats so that we can get started. I guess I have to tune this down a bit. That should work. All right, I hope the sound is okay for those following us on the live stream. Please let me know if it's not. Just write a comment to tweet back. Good. So there's still plenty of seats over here and also up there, if you'd rather have a few from up there. So let's get started. Welcome to this class in Mathematics 1, everybody. As usual, we'll start with a very quick warm-up question. Let's see. Here it is. Available on TweetBack. True or false question again. For each bimatrix game, the payoff matrices of both players are square matrices. Is that true or not in general? I'll give you one more minute. All right, so 5 seconds. We can take a look at the results. So here is your vote. Most of you said the payoff matrices of both players are square matrices. That is true, and most of you are wrong. I guess the question was a little mean. Most of the examples that we've seen so far, all of the examples that we've seen so far do have this property. And that is because in the examples that we have seen, both players usually have the same set of strategies. And that will actually be the case for, I guess, all of the examples that we will be looking at. But it doesn't have to be that way. It could very well be that one player has a certain set of strategies and the other has a completely different set of strategies. And of course, that may be larger or smaller. And in that case, the payoff matrices wouldn't be square matrices. They have to be of the same size, both matrices, but they don't have to be square. Right? And that property depends on the number of strategies that the players have. So in general, this is false. All right, so let's start with today's topics. Can you read that okay? Good. One thing I'd like to announce is exam registration. Exam registration is open. It has been so for a few days already. A couple of you have already discovered that and registered for the exam. So please remember, if you want to take the exam for this course, you have to register for the exam on TUM online. And there usually is no possibility to register after the deadline. Depends a little on how your school is handling this, but as far as I know, your school will not allow any late registrations. So please remember to register. The deadline is the 15th of January at midnight. So that's the last day where you can register. However, you can deregister from the exam up to 7 days before the exam date. So it doesn't hurt to register now, and if you change your mind later, you can always deregister. All right, and that is for the examination on 12th of February 2024. For the retake exam in April, there will be a separate registration during the semester breaks. So that will only open once the first exam has been corrected, obviously, so you know whether you need to take part in the retake or not. And just to repeat that, you are free to just do the retake and not take part in the first exam if you want to do so. However, there will not be an opportunity to take this exam in the summer term. So your next opportunity will be this February exam, then the April exam, and then it's a year until probably next February for the next opportunity to take this exam. Okay. So let's talk game theory. You do remember that we introduced bimatrix games yesterday, and we've also talked about the concept of Nash equilibria. And just to remind you, a Nash equilibrium is basically a set of strategies where no player has an incentive to choose a different strategy, given that the other player stays at their choice of strategy. Yeah? So there's no incentive to unilaterally choose a different strategy from that point on. And there always is a Nash equilibrium in mixed strategies. There may also be one in pure strategies. There may be more than one Nash equilibrium for a given game. But there always is one in mixed strategies. And today we'll be talking about a specific class of bimatrix games that we call matrix games. And we'll be able to do some more analysis of those. First definition, we've already briefly touched on that yesterday. If we have a bimatrix game where the two matrices, AR and AC, the payoff for the row player and the column player, where these matrices are closely related, and by closely I mean one matrix is the negative of the other, then we'll call this a zero-sum game or a matrix game. And matrix game is the name I'll usually use from this point on. The striking property of this is basically this is a game where one player wins what the other loses. So imagine you're playing something for money and the loser has to pay to the winner. That's a zero-sum game, right? The sum of payoffs is always zero. The gain of one is the loss of the other. So in the sum it's zero. That's where this name comes from, zero-sum game. And then a matrix game comes, of course, from the fact that, well, if I have this property, it's enough to provide one of those matrices to have all the information necessary for the game. And which of these matrices you want, basically that's just a matter of convention. In this course, we'll always use the matrix AC. So the column player information will always be displayed in a matrix game. If you want the row player information, you'd have to take the negative of that matrix. Again, that's just a convention, and in several books you'll find using different conventions. But in this course, we'd always use the column player's payoff matrix. I think I should tune this down a bit more. Give me a second. Let's try that. All right, so from now on, we'll concentrate on matrix games. And specifically for matrix games, well, almost the same as for bimatrix games, we can have a look at the expected payoff if we know the strategies of both players. So again, let's say we have a strategy X for the column player, a strategy Y for the row player. Then the payoff of column is given by this expression. Remember, A is the column player's payoff matrix, so that's the same thing that we always used. Only difference is we word A instead of AC now. Right? So this is the column player's expected payoff given the strategies Y and X for row and column. The column player tries to maximize this. Right? This is his payoff, or he will get. So his goal is to maximize that payoff. The row player, of course, gets the negative of that payoff. So in other words, he has to pay what the column player gets. So you could also say the row player's goal is to minimize that payoff, or to maximize the negative of that. Right? So the column player wants a maximum possible payoff. The row player is interested in minimizing the payoff. Ideally, the payoff will become negative for the row player because then he gets paid something. And again, you can characterize what a Nash equilibrium means in that situation. A pair of strategies is a Nash equilibrium if and only if no player has an incentive to deviate from his or her current strategy. So this here would be the payoff in the equilibrium situation. Remember, the row player wants to minimize that. So if this inequality holds for all possible strategies Y of the row player, that means for every other strategy the row player could use, this payoff will be at least as big as this one here. The row player wants to minimize the payoff. So this is a minimum for row, given that X plays X star, right? So that's this condition, and this is the condition for the column player. The column player wants to maximize his payoff. So for any other strategy, column's payoff is less or equal to what he gets in the Nash equilibrium. Right, so you can change that characterization from the two inequalities we've had before to this, basically this chain of two inequalities. All right, so here's a quick example of a matrix game, and most of matrix games will look something like that. We have two players. Again, in most cases, they'll have the same set of strategies, but that is not necessarily so. There may be other examples. So here, row and column both simultaneously show either one finger or two fingers. Right? So they count to three, then they show either one finger or two fingers. If both show the same number, so both show one or both show two fingers, then column wins. So in other words, if the sum of fingers is even, then column wins and gets €1 from row. And if both show different numbers, so the sum of fingers is odd, row wins and gets €1 from column. Right, so that's a classic zero-sum game. One player gets what the other pays. So here's the payoff matrix for that game. Remember, we look at this from the point of view of the column player. And remember, the column player wins. Column wins if both show the same number. So both show 1 or both show 2. So these are the two situations where column wins and gets a euro. These are the two situations where row wins, so column loses. So column pays a euro. So that means his payoff is -1. Right? So again, we can ask ourselves, is there a Nash equilibrium in that game? And let's first have a look at the pure strategies before we do something else. Well, if we look at, let's say, this first column here, say column plays this. If row knows that column plays this pure strategy, what is his best response? Remember, row wants to minimize. So row will play this row here, right? And then they would meet at this point, -1. Is that a Nash equilibrium? Well, obviously, row doesn't have an incentive to change his strategy, but column has, right? If column changes to this here, and row stays at the second row, then this will be the new point, the new payoff point, and that means column wins. Right? So there is no Nash equilibrium in the first column. Let's look at the second column. Again, let's say the column player chooses the second column, then the row player will obviously choose row 1, because then they will get to this point here, and row wins a euro. However, column in this situation will have an incentive to change to column 1, because that is when he will win a euro, right? So that means there is no Nash equilibria in this game in pure strategies. And of course, you know there always is a Nash equilibrium in mixed strategies. So if the exam question would be, is there a Nash equilibrium? Your answer would be yes, because of the theorem. All right. Well, basically, we also try to compute that Nash equilibrium in mixed strategies by computing the expected payoff. So we just said that row plays this strategy, column plays this strategy. Remember, strategy is always a vector with entries between 0 and 1, and the sum of all entries is 1. Right? So it's a probability distribution over the possible actions. So if action 1 has a probability of y, then necessarily the second action must have a probability of 1 minus y, because there are just 2 actions. That makes things a little easier. And then basically we can compute the expected payoff and see if we can infer something about the optimal strategies for both row and column player from that. And if we do this, we found we get to this point here, so that is the expected payoff for those general choice of strategies. So what is the optimal strategy? Well, what we can see here is the column player will, of course, want a positive payoff. Right? So column player can only influence this part, because X is the column strategy. He has a choice of either making this 0, or positive, or negative. Of course, he will not want to make it negative. He's not interested in a negative payoff. He could make it positive. If he does, however, the row player, that has the same expression here, right? So the row player can influence only this expression. And remember, the row player is interested in minimizing the expression. And again, he can choose to make this part of the expression 0, positive, or negative. So if he knows that the column player makes his part of the expression positive, he will react by making this negative and winning something. On the other hand, if the column player chooses to make this part here negative, then the row player will make this positive and again win something. Right? So if column chooses to make this positive or negative, then he'll always be outplayed by row. So his best choice, obviously, is to make this 0. That means he can ensure at least not losing anything. And the same is, of course, true for the row player. Right? So that's a pair of best responses, and that means we have a Nash equilibrium and an optimal strategy. And well, the choice of strategies that you need to make this 0 is 1/2 and 1/2. So basically you flip a coin. You randomize it, whether you show 1 or 2 fingers. And in this case, that's true for both players. That doesn't have to be the case. Right? In many examples that we see, the games are somewhat symmetric in that both players have the same set of strategies and the payoffs are symmetric in a certain way. So often you'll find the optimal strategies will be the same for both players. But that depends on the setup of the game. That doesn't have to be the case in general. All right, so the payoff in this situation is going to be 0, and this choice of strategies is a Nash equilibrium for this parity game. Now, in this case, we were lucky that the expression for the payoff, for the expected payoff, was so easy that we could analyze this by just looking at it. Generally, that might not be the case. So the question is there some way to compute optimal strategies in general and the Nash equilibrium? And the answer is yes, there is. So if you want to talk about optimal strategies, here's what the players will want to do. If column plays a fixed strategy, then row will, of course, react to that, and row will play his best response to that strategy. Best response means row will look at the expected payoff given that X star, and he will minimize that over all row strategies available. Of course, column knows that. So column needs to choose an X star strategy that after this minimization yields the worst possible outcome for row, or the best possible outcome for column. Right? So what column does is he maximizes this minimum. Now, it does sound a little complex at this point, but I hope it will get easier. And of course, row does the same thinking. And for him, the roles are reversed, basically. So here, given a strategy for the row player, the column player will maximize the payoff, and row knows that. So row will minimize for this. Row will minimize this maximum. And it turns out that for a matrix game, those expressions are equal. Right? And that's a property of a zero-sum game, right? I mean, what we've inferred so far about this minimax, maximin problems, those all rely on the notion of a zero-sum game. So you can't use that for general games. It's only true for zero-sum games in general. Okay, so those are equal. And the game admits a pair of strategies that realize those numbers, and those are called optimal strategies. Those are the strategies that rational players would choose. And finally, you can show that the notion of optimal strategies and Nash equilibria is basically the same thing. So for a matrix game, a pair of optimal strategies is always a Nash equilibrium, and vice versa. Any Nash equilibrium will be a pair of optimal strategies. Okay, so instead of computing Nash equilibria, you can try to find an optimal strategy. And here's how you can do that. And I hope you are familiar with expressions of that sort. Those are linear programming problems or linear optimization problems. I don't know which term you used. Linear programming? Okay. So what is happening here? This here is the problem from the point of view of the column player. The column player is interested in maximizing the payoff, right? The payoff that we will get will be encoded in this additional new variable. We call that new. So column maximizes this new. Now, how can column make sure that he will get that payoff? So here's part of the payoff expression, right? So that's basically the part that column can influence. Column can influence this X strategy. And then AX is the expected payoff for each possible action of the row player. So that's a vector that has several rows, one for each action the row player could choose. And each row contains the payoff that row, or that column would get, if row chooses that row. So what column wants to do is, he wants to make it impossible for the row player to find a move that gets him a worse payoff. He wants to make sure that he will at least get a payoff of new. And how can he do that? Well, basically, he can do that by making sure the row player always has to accept a payoff of at least new, no matter what action he chooses. And that is encoded in this inequality here, or rather in that form here. Yeah, so this is the expected payoff given that column plays X for every possible action of the row player. And that means every row is at least new. So no matter what pure strategy row would choose, the payoff would be at least new. And of course, if row chooses some combination of pure strategy, some mixed strategy, then again, the sum would be at least new. Maybe higher, but new is the minimum that the column player will get. And he's searching for the maximum possible new where he can guarantee that. And these two, basically those just encode that, well, all X entries are non-negative and the sum of the X entries is 1. So that just means X is a strategy. Row player solves basically the same problem. Row is choosing a strategy called Y. So again, this encodes that Y is a strategy. The row player is interested in minimizing the payoff. So here we call the payoff mu, and he minimizes that. And from his point of view, well, this is the part of the payoff he can influence. And he needs to make sure, remember this here will be a vector, a row vector, so we have several columns in that vector. He needs to make sure that each column is bounded above by mu. So for each possible action of the column player can get a payoff of at most mu. Right? So this is what the row player wants to ensure. And now to find optimal strategies, what we have to do is simply solve those two LP problems, and we're done. And you all know how to solve LP problems, so that's it. It's not more difficult than that, really. All right, one more definition, or two more definitions. Once we have an optimal strategy, of course, we can compute the expected payoff in that optimal strategy, and this expected payoff is called the value of the game. So basically, that means if both players choose their optimal strategies, this is the payoff that column gets. And the game is called fair if that value is 0. So basically, the idea here is the value is the expected payoff if the game is repeated over and over again with those optimal strategies, which might be mixed strategies. So in the long run, on average, column will get that value as a payoff. And the game is fair if the payoff is 0, so none of the players has some advantage. In the long run, it will all even out. That's the idea here, right? And please don't confuse this with the notion of zero-sum games. A zero-sum game does not necessarily have a value of 0. Yeah, that's an additional property the game might have. All right, so we'll not look at this example. We do another one instead. You can look at this in the video. Actually, let's do another one. All right, so this is basically matrix games. There's one more special part about this, but we'll talk about that later on. Let's first take a look at one possible example, and you already did take a look at one example, hopefully, at home. And that is this here in exercise homework 6.2. Consider a matrix given by this payoff matrix here. And I was asking you to determine the value, the corresponding optimal strategies, and the Nash equilibrium. And of course, you know, if you have the optimal strategies, you also have a Nash equilibrium, and you also have a value. So that's what you want to do. Determine the corresponding optimal strategies. Right. So, question, did you actually solve this? What value did you get? And how difficult did you find this? Again, let's take a quick look on TweetBack. I didn't want to show that. Yeah, that's better. And for the solution, I'm also interested in whether you used linear programming and the simplex algorithm, or whether you used linear programming but didn't need the simplex algorithm after all, or whether you used some completely different approach. All of that should be possible. I'll try. Okay, 20 more seconds, and then we'll close the vote. All right, so let's first have a quick look on how difficult you rate this problem. And I'm not surprised, I'll have to admit. Most of you found this pretty hard. Let's see how you solve this, or how you think you solve this. A slight majority didn't solve it at all. Most used some approach that is not linear programming, and some used linear programming, some even used the simplex algorithm. So we maybe will have a look at that today, just to show you how that is done. And let's see what value you got, finally. So what's the value of the game? Most of you found a value of 2, obviously, right? 5 is a close second, and there's 0, and the others are pretty far away from that. Okay, so the right answer, if I have not been mistaken, would be 5. But we can verify that together. All right, before we go over this, maybe let me just answer a few questions that have popped up, just to clarify those things before we move on. One question is, every pair of optimal strategies also a Nash equilibrium? And the answer is, for matrix games, yes. And that's an if and only if. So a Nash equilibrium is a pair of optimal strategies, and vice versa. Then someone is asking, why does the role player want to minimize the expression? Does he not want a good payoff? The point is this payoff matrix A is from the point of view of the column player, right? So if we compute the payoff with that matrix, we get the payoff of the column player. The row player's payoff is the negative of that. So the row player is interested in minimizing that because he wants a good payoff. If that payoff is low, he doesn't have to pay a lot. If that payoff is in the negative numbers, he even gets something. And minimizing, of course, could also mean getting a negative number, right? The more negative, the better for the row player. So yes, he is interested in minimizing that expression because he wants a good payoff. And finally, are there no zero entry? No. Are no zero entries and some entries are 1 the only constraints for the LP? Let's look at the LP once again. Here we were there, right? Yeah, so there's the LPs. Maybe it's not immediately clear what I mean here. So this here says all entries of that X vector have to be at least 0, so there's no negative entries. 0 is fine, but any positive entry is also fine. This expression here, maybe that's not immediately clear. What I mean by that is the sum of all the xi's is 1 from 1 to n, right? So the entries of that vector sum up to 1. And of course, those two together implies that no entry can be larger than 1, right? The sum is 1, and there's only positive summons, so no single entry can be larger than 1. And those together say, well, X is a vector that gives a probability distribution over the set of possible actions of the column player. Okay, so it's not no zero entries. Zero entries are fine, those are allowed. And it's not some entries are 1. One entry may be 1, or there may be some probability distribution, possibly all entries are non-zero. That's also fine as long as they sum up to 1. Okay, so I hope that clarifies that. All right, so let's maybe take a look at this problem here. Where do I have it? Here's sheet 6. Maybe also answer that next question. So we're interested in solving the question, what are the optimal strategies for that? What is the Nash equilibrium? And what is the value of that game? And for the value, I'd say you could already take a quick guess. Looking at that matrix, you'll see that all entries are strictly positive. So that means whatever the outcome is, the column player will always get something. The row player will always lose. So the value will have to be positive. And that means the column player does have an unfair advantage in that game, simply because he always gets something and the row player always has to pay something. Right? That means that is not a fair game. The value can't be 0. And you know that immediately from looking at that matrix. Now, maybe let's copy that. Here it is. Copy that to my notes quickly. And take a look at, oops, those are the wrong notes. Sorry. These are the right ones. So let's take a look at 6.2. Let me just copy the matrix first. And now let's say we want to find out whether there is a Nash equilibrium in that matrix. Then one possible strategy would be to first see if we can find an equilibrium in pure strategies. If that is the case, then we also have a pair of optimal strategies and we don't need to do any more computations. Right? That might work. If it does, it's probably the best and shortest way. If it doesn't work, we can always go on and do the LP. So let's take a look at that. Let's first take a look at the column player. The column player could choose this or this column. Let's say he chooses this column. What would the row player do? Well, the row player is set to minimize the outcome. So if we are, let me actually use a color here. So if we are in this column here, then the row player will want to choose the first row. So we will end up with this entry here. However, in this position, the column player would rather play column 2 instead of column 1, because that would mean he gets 5 and not just 1. So this can't be a Nash equilibrium, right? So no Nash equilibrium in column 1. Let's look at column 2 next. For column 2, again, if the column player chooses this strategy, just play column 2, then what will the row player's best response be? Well, the row player wants to minimize the payoff, so what he'll do is he'll choose row 1 again. Obviously, that minimizes his payoff. So that means we'll end up at this point. The row player doesn't have an incentive to change, because he'd pay more. The column player also doesn't have an incentive to change, because he'd get less if he does. So it turns out this point here, that actually is a Nash equilibrium in pure strategies. And that means we have a pair of optimal strategies. So the pair of optimal strategies. And we usually write those in this order: first the column player, then the row player. So that pair of optimal strategies for column is play the second column, so that's the strategy 0, 1. And row plays the first row, so that's 1, 0. So this is a pair of optimal strategies here. And we can also use the value of the game. The value is the expected payoff in this Nash equilibrium. And of course, well, it's pure strategy, so the payoff is exactly 5. And that also means the game is unfair. In fact, it's biased in favor of column. Right? So column gets 5 in this case. Okay, so that's probably the quickest way of solving this. And some of you already asked about this, so let me quickly discuss that part. If you look closely at a matrix, you can see that's even easier to get, because if you compare those two columns, you can see that playing the second column is always better for the column player, right? No matter what row does. For every row, the second column is always the best choice. So that means that second column will always be chosen by the column player. There is no incentive to choose the first column. If we have an action like that, then this is called a dominating action. It would be a dominant strategy to just play this and nothing else. Right? So it's always better no matter what the other player does. Same is true for the row player in this case. So again, row minimizes. And if you compare the two rows, you'll see that the first row is always less than the second row. So that means playing the first row is the dominant strategy for the row player. And if both players play their dominant strategies, then again, we'll end up in this point. Right? So sometimes you have something like that. Not very often, because those games are too easy. But of course, if you have something like that and you recognize that, then you can use that. Let me just take this question. What would be the value for two Nash equilibria In a matrix game, they will always be the same, right? So the expected payoff is always the same no matter which equilibrium we choose. And that's something that we've discussed before in this. This is contained in this theorem by von Neumann, actually. All right. One more question I'd like to answer. Could you explain why the column player doesn't choose 1, 2? So why would the column player not choose this point here? And the answer is because he can't. Of course, he would love to be there, because that gets him the best payoff he could hope for. But the column player can only choose a column. He can't choose a position in the matrix. So what he can do is, he can choose this column. And then the row player will choose a row. Right? So that's not a decision the column player can make. And of course, if the row player knows the column player chooses this second column, the row player will choose the first row, because that means he has to pay less. Right? So each of the players only has a limited ability of choosing the outcome of the game. One player chooses the column, the other chooses a row, and the combination of both actions determines the outcome. It's not that one player could choose the outcome. Right? That's just not possible. Right, and where do we know from that column maximizes and row will minimize? Well, as I said, the payoff matrix in a matrix game is that of the column player, and the column player will want to maximize the payoff. And it's a zero-sum game, so whatever the column player gets, the row player will have to pay, and vice versa. So that means the row player is interested in minimizing what the column player gets. And if that value is negative, then he gets something from the column player. Again, that's just the convention that we've used here. So we always use the column player's payoff matrix. We could have done that differently, and then the roles would be reversed. Yeah, but one player is always maximizing, the other is always minimizing, because one gets and one has to pay. And of course, those payments could be negative if it's reversed. Maybe this question before we get to the rest. Why does column choose the position first? He doesn't. So the point is both players make a decision according to their strategies simultaneously and without communicating to the other players. It's just that for the point of analyzing the game, I usually look at those situations separately. So I often say, assuming column player chooses column 1, then what would the row player do? And then assuming column player chooses column 2, then what would the row player do? So what is the best possible strategy for the column player? Would he choose 1 or 2? Or a mix of both? Right? So it's just easier to kind of talk about that one after the other for the analysis of the game. Of course, in reality, both make their choice simultaneously. But they always, before they do, they think about what would the other player do if I did that? And how can I prevent that from being a bad outcome for me? Yeah, that's why they go through, basically they solve these optimization problems before they make their choice. And sometimes their choice will be to just randomize and play a mixed strategy instead of a pure strategy. Thanks a lot. I know it's late. But maybe I can get you to work a little bit. So this is probably the easiest way of solving 6-2. Of course, you could also solve that through the linear programming approach and the simplex algorithm if you want to. I'd rather discuss that with a different example, so that you have one more example that you can look at. The details for solving this with a simplex approach will be in the suggested solutions that you get for that sheet. So let me give you another example we can practice this simplex approach on. And that is called penalty kick. All right, so let me explain the game briefly. We're playing soccer, and in soccer, there is a penalty kick. That means we have a penalty taker that tries to kick the ball into the goal, and we have a goalkeeper that tries to make sure the ball will not enter the goal. In a very simplified setup that we will be looking at right now, basically both of these have two possible actions that they could play. The penalty taker could either aim for the left part of the goal or for the right part of the goal. And the goalkeeper needs to react very, very fast. So let's assume he will not be able to see what the penalty taker is doing, and he has to choose which part of the goal he will guard before the penalty taker is actually doing the kick. Yeah, so those happen simultaneously. No one can react to anything the other person does. So the goalkeeper also has two strategies. He can guard the left part of the goal or the right part of the goal. And let's also assume if the goalkeeper decides to guard the correct part of the goal where the penalty taker is aiming at, then he will be able to prevent the goal, and otherwise the penalty taker will get a goal. Right? So very, very simplified setup. We have this penalty taker that can either kick to the left or to the right. So we'll say the strategies are either L or R, left or right. And we have the goalkeeper that guards the left or the right part of the goal. And now if both make the same decision, that means the goalkeeper will be able to avert the goal. If both make different decisions, that means the penalty taker will be able to get a goal. Right? So the combination left-left or right-right means no goal. The combination left-right or right-left means there will be a goal. So first question is, what does the payoff matrix look like? And let's say we just count goals for the for the penalty taker. So we'll do this from the point of view of the penalty taker. So he could either get a goal or not. So maybe take 2 minutes to think about that, and then we'll go on with our analysis of that game. All right, I'll guess you're done. So let's take a quick look at what that payoff matrix will look like. Obviously, we have two strategies for each player, right? We call those left and right. The goalkeeper is our row player, and the penalty taker is our column player. So what is the payoff for this left-left situation? -1, you could say that. I'd rather say 0. But -1 is also fine. It's just that the numbers in my analysis will differ a little. You could also do that with -1. That's fine. Right? So I just want to say the penalty taker gets nothing if he doesn't get the ball into the goal, right? So that's a 0. But again, -1 is also fine. And of course, the same is true for right? So again, if both choose the same strategy, then the penalty taker will not be able to score a goal, so he gets nothing. And then what is the payoff in the other two situations? Well, of course, in that situation, the penalty taker will be able to score a goal, so that means he gets a payoff of 1. Right? And again, of course, that 1 is kind of arbitrary, just needs to be some positive number, and it should be the same in both situations. Okay, so we work with that payoff matrix here. Next question. Does the game possess a Nash equilibrium in pure strategies? If it does, that would of course be the easiest way to solve this, so let's take a look at that. And again, I'll give you 2 minutes to think about that. All right, that should be sufficient. So let's ask, does the game have a Nash equilibrium in pure strategies? Again, the question is on TweetBack. I'll give you 30 seconds to answer it. Right, nice. So the answer is obviously no. It doesn't have a Nash equilibrium in pure strategies. All right, I guess I don't need to talk about that. So let's get it right to the next and probably most interesting question. Can you find a pair of optimal strategies? So how do you do that? And I already said, in this case, I'd like to take the approach of trying to take a look at the linear programming problem. So let's give that a try. So remember what were those? Let me just copy those LPs so that we have a reference. I'll just do this one here. Copy that here. And let me erase all that stuff we don't really need. Okay, so that's the LP here for the column player, and we'll only solve that for the column player. We'll work the same way for the row player. So in this specific case, how does that look? Well, we want to maximize the payoff, so we call that new. Again, new is a variable in our LP here. And we want to maximize that under the condition that AX is greater or equal to new for all rows of a matrix. So we'll call the strategy of our column player, of our penalty taker, X1, X2, right? Or XL, XR. Let's use XL, XR. It's probably nicer. And if you look at the matrix, well, in the first row, what happens there? Well, if we play XL and XR, that means we choose this column with a probability of XL and this one with a probability of XR. Then if the row player chooses this row, the payoff will be 0XL plus 1XR. Right? So we get 0XL plus 1XR, so that means we just have XR. Let me write it in this way for once. XR is greater or equal to new. And for the second row, we get XL is greater or equal to new. Right? And that means the row player will now choose one of those rows, and no matter which row he chooses, we always have a guaranteed payoff of new. And we want to maximize that possible guarantee, right? That's the idea of that LP. And of course, we also have to add the condition that we have a strategy, so XL and XR sum up to 1. And, sorry, XL and XR are greater or equal to 0. Right? So that's the optimization problem. And now one way to solve this would simply be to take a good look at that problem, reformulate that a little. You can use that equation here to get rid of one of those two variables. And then just have two variables, and by looking at it, you should be able to devise what the optimal solution could be. But just to show you how you could do it in the general situation, I'd like to try and solve this using the simplex algorithm. So I do hope that my way of solving the simplex algorithm is the same as the one that you discussed in your course. Let me know if it's not. I used the lecture notes to devise that. It was correct a couple of years ago. I hope it still is. So first thing we do is we reformulate that to get that into the correct form. And the correct form is one where you only have equations, or equalities, and greater or equal to 0 constraints. To do this, we don't have to do anything about the objective function just yet. We have an inequality constraint here. And more precisely, this can be written as nu minus xr is greater or equal to 0. Or if you want to turn this into an equality, oh no, sorry, I should use the other way around. My bad, is less or equal to 0. So if you want to turn this into an equality, we'd have to add a slack variable to that. So what we can do is we turn this into an equality by adding a slack variable. I'll call that as 1. And then I can say this is equal to 0, right? So basically the idea is this is less or equal to 0, so I can just add whatever the gap is to get to exactly 0. Right? And that gap is always positive or 0. Right? So I get this new variable here. And I can do the same thing with this equation. So nu minus xl is less or equal to 0. So I can add a possibly different slack variable here to get that to be equal to 0. This equation here already is an equality, so I don't need to do anything about that just yet. And then all these variables here are greater or equal to 0. Two more things I need to take care of. First, I also have this variable nu in here. And that is not constrained to be greater or equal to 0. That might become negative. You could argue that it doesn't in this case, but I'd just like to give you an approach for the general case. And for this formulation, we'd like to have this condition for all variables. So we'd have to replace this variable here by two variables. Basically, we just split it up into a positive and a negative part. We call that mu plus and mu minus. And the idea is that, well, let's say if mu is 5, mu plus will be 5 and mu minus will be 0. If mu is minus 2, then mu plus will be 0 and mu minus will be 2. So we can split this up in positive and negative parts. And then both of these are greater or equal to 0. Right? That way we can map that into this two-variable situation. So program becomes slightly more complicated, but again, we're back in the right form. And finally, we need to find a solution we can start off with. And one possibility is usually to set everything to 0 and then use the slack variables to get a valid solution. In this case, it's not necessary to do it this way, but again, I'll do that to be able to cover the general case. In two of these equations, we already have a slack variable, so we can just say, well, we'll set all of these to 0, and then S1 will be the right-hand side, and incidentally, that is also 0, so we're good. In this case, if we set these two to 0, of course, we'll need to also introduce kind of a slack variable here. So that's an artificial slack, if you want. We'll just introduce that for the sake of getting an initial feasible solution easily. And then we can just set that as 3 to be equal to 1, and we'll have our initial feasible solution. And of course, that is also constrained to be greater or equal to 0, so I need to add that here. And I think that should be all. That's usually called, what is usually called? It's different, unfortunately. What did you call that? Canonical form? Natural form? Sorry? Standard form? Standard form. Okay, good. So I'll try to call it standard form. Unfortunately, the terminology is not quite fixed at this point. All right, so now we have standard form. And that means now we can turn this into a simplex tableau. And we can start doing our computations. Question? Could you please be a little more quiet so I can understand the question? So you mean for which constraints? For these here or these here? You mean you have to split this thing? Oh, in the constraints themselves. Yeah, you're right. Of course, I should split this up as well. Yeah, thanks. Yep, I should do the split up here as well. So let's replace that mu by mu plus minus mu minus everywhere. I think that's the only places it appears. Thanks. All right, so this is standard form. And I'll try not to make a huge mistake. Let's see if I succeed. Unfortunately, I haven't written that down before. I should have done that. Okay, so we want to put this into the simplex tableau so that we can do our computations. I hope my simplex tableau looks somewhat alike to your simplex tableau. Again, it's not standardized in any reasonable way, so that might be a little different to what you're used to. So what I usually do is I write down the basic variables first in the column of their own, just the names of those basic variables. And of course, we'd have to fix what the basic and non-basic variables are before we start. I already said we basically have these slacks that we can play with to get our initial feasible solution, so that will play the role of our basic variables. And just to make sure that it's all correct, we have, let's see, 1, 2, 3, 4, 5, 6, 7 variables. We have 3 equations. So to get a unique solution, we would require 7 equations, right? 7 variables, 7 equations. That would enable us to obtain a unique solution. There is 3 equations in the system already. So in addition to that, for a unique solution, we need to set 4 of those to be equal to 0. Right? And those will be the non-basic variables. So if I choose these 3 as basic variables, these 4 remain, and those will be the non-basic variables then. Okay, so let's go with that. And of course, that's the usual choice. In the beginning, you always use the slack variables as basic variables. So let me just write those down. S1, S2, S3, those are my basic variables. Then in the next column, I'll usually write down the value of those variables. And in the next few columns, I'll write down the actual simplex tableau. And let me see. I usually have 1 column for each variable. Again, not standardized. Some people only keep the non-basic variables here. I tend to keep all variables so that it's easier to switch tableaus. Yeah, but it doesn't really matter. So we have XR, we have XL, we have mu plus and mu minus, rather that way. And then we have the S's, S1, S2, S3, and that should be it. Okay, we're maximizing, so we're putting minus the objective value in that last row, and that is often denoted by C, the objective value. I don't know if you also do that, just a convention. If you don't like that C, just omit it. We didn't really do anything with that. The starting values for our basic variables, I already said that, will be 0, 0, and 1. 0, 0, and 1. And all the non-basic variables are set to be 0, right? And that way we have a feasible solution, because if everything is 0 and S3 is 1, then this will be 0, this will be 0, this will be 1, and well, all of these will be satisfied as well. Right? And I would just copy the numbers into this tableau here. So for the first row, we basically use this in equality here that doesn't have an XL. It has a minus XR. It has a plus nu and a minus nu, a plus S1 and no S2 and no S3. The second row will be composed of this here. So here we have a minus XL, we have no XR, we have, a 1 for the new plus, a minus 1 for the new minus, and a 1 for the S2. And for the third equation, this one here, we have XL, XR, none of the news, and S3. Right? And of course, it's important to have these here correspond to the entries here on the left, right? So the basic variables, those correspond to unit vectors in the columns, and the 1 always points to the value on the left. Okay, finally I need the objective function, or better, the reduced costs. So this goes into the last row. Sometimes people also put it in the first row. I don't know what you did. Last row, first row? Last row, great, okay. So the objective is mu plus minus mu minus. So that means we'll start with the 1 here and the minus 1 here. And then there's one more thing we need to take care of. And that is we need to get rid of that S3 entry here, right? In the solution that we want, the S3 actually has to be 0. Otherwise, this equation wouldn't be satisfied. So to be able to do this, we use what you hopefully call the big M method. The idea is to put that S3 into the objective function and penalize it, hugely. So basically what we do is we add something like minus M times S3 to the objective. And that M is very, very large. So we make sure that as we subtract it, that means the maximum solution, as long as we have S3 in there at a positive value, will be very, very low, and we don't want that, so the best we can do is set S3 to 0 to get rid of that huge term. Sorry? Why do we not just do minus S3? We want to be sure to get rid of that. And it might be that it's still a good choice if you just do minus S3 to keep that in there at some positive value. Right? I mean, we have coefficients of 1 here, and if we have one of the same size here, then there might be some sort of interplay between those two values, and it might be a good idea to keep S3. But we don't want that. Right? So that's why I put a very huge value in there to make sure it will be gone in the end. No optimal solution can have a positive value of S3. That's the idea. Question? So you could try to do so you want those two, and which coefficient? 0? We'll do that. Give me a second. So I want the minus M here, and nothing else appears in the objective function, so all the other coefficients here are 0 at this point. Right? And we also put a 0 here for the moment. Now, first step, we need to compute the actual reduced costs before we actually start the simplex. And for that, we need to make sure that for the basic variables, all of these coefficients are 0. Right? That's the rule. For basic variables, the reduced cost coefficient is always 0. That's not the case because of this minus M here. So first step we need to do is we need to make sure we have a 0 here. Right? So that's kind of a preparation step before we start the actual simplex algorithm. And to do that, we use the corresponding basic variable. And basically what we do from now on is we do Gaussian steps, Gaussian elimination steps in the simplex tableau, more or less. And if you want to get a 0 in this position using this column, well, here's the only pivot element that we have. So what we do is we add M times the third row of the simplex tableau. And by third row, I mean this one here. Right? So I just count those rows here. Okay, so we do that. And to make things a little easier for me, let me just copy this whole thing. All right, so if we do that, we'll of course get a 0 entry here. That's what we wanted. Here's 0, so nothing changes for these entries. Here we have 2 1s, and here as well, right? So what happens here is we get a big M instead. Here, and also here. We get an M. Maybe I can write that in a way that you can actually try to read. Okay, so this tableau here, oops, that should be our starting point. And now what we have here in that last row are the reduced costs. So basically the reduced costs tell us if we include the corresponding variable in the basic variable selection by a certain amount. And basically this is by how much the objective function will change if we do this. Right? So if we would be able to include XL at an amount of 1, the objective will change by big M. If we include mu plus by an amount of 1, the objective will change by 1, not surprisingly. Right? And these effects might either be direct, as they are in this case, or they might be indirect, because changing XL will also change other variables, and those in turn influence the objective function. That's basically the information that we get from this reduced cost row. We want to maximize, so we're interested in the reduced cost entries that are positive. Right? Positive reduced cost means we can increase the objective, and that's what we want to do. So we want these variables in the basis, because having variables in the basis means we can increase them to be larger than 0. Non-basics are always 0. Basis variables may not be 0. Okay, so that's what we want to do. Have I copied this? Just to be sure, let me copy this again before I draw into it. Let me just make a quick copy for the next step. So we need to choose a variable that has a positive reduced cost entry. It doesn't really matter which we choose. There is no prediction of how long the algorithm will take if we do this or that. Usually one chooses an entry that has the largest possible reduced cost entry, but that choice is up to you. In this case, the largest reduced cost entry is one of those M's here, so we could choose XL or XR. I'd say let's just go with XL. So that means, maybe let me mark that instead. So we choose this column here. That means you want to get this XL variable into the basis. Right? I'll signify that by drawing an arrow up here. So that means I want XL in the basis. I will enter the basis. And of course, in exchange, one of the other variables has to leave the basis. To be able to find out which one that is, I'll have to find out by how much I can increase that XL before one of the inequalities or equations will be violated. And this is basically what these entries and these entries tell me. And I'm not going to explain the rules behind all of this, but what the procedure does is it identifies the positive entries, and there's only one positive entry here in this column. And then we'd compute the ratio of this value to that. So in this case, don't have to do that because there's only one possible choice. The ratio here would be 1/1. If we had more than one choice, we compute that ratio and choose the one with the minimum ratio, because that's the first one that will stop us, basically. Okay, so this here is going to be our pivot element for the next simplex step. And that means the corresponding row here contains the variable that will leave the basis. So S3 will leave the basis at this point. And that looks good. We wanted S3 out anyway, right? And what we do now is we'll make sure that this column here becomes a unit vector with a 1 at this position and zeros everywhere else. And to do this, we just use Gaussian elimination. We have a 1 already, so no need to do anything about that. We have a 0 here. That's also good. So only thing we need to change is this -1 here. And for that, what we'll do is we'll just add the third row so that we get a 0 in this position. Oops. So let's do that. So that means we are changing the third row. The second row, sorry. We keep the S2. Don't forget to also do this operation for the values column. So here, if we add this, we get a 1 here. We get a 0 here. We get a 1, a 1, a -1. Nothing changes here. We get the 1 here, and we get a 1 here. I hope that's all correct. Then for the row that contains the pivot, all we have to do here is change that entry here on the left. So that is not S3 anymore. Instead, that is now going to be XL. And then we also have to take care of the reduced cost row. And again, we do the same thing as we did before. We need to make sure that the entries below the basic variables become 0. So what we need to do here is we need to subtract m times the third row from the reduced cost row. Right, and what happens there is, let's see, here we get 0. Here and here we also get zeros. Here we keep the 1, here we keep the 1, here we keep the 0, here we keep the 0, and here we have this 1 here, so that means this becomes a -m. And if you detect any mistakes, let me know immediately. Otherwise, this will all be moot. Okay, so first simplex step. Things are looking good already because we have the S3 out of the basis. We got the XL into the basis. Of course, the expectation is that XL or XR, or maybe both, will be positive, so they should become part of the basis at some point. And the value of the objective is down to 0. All right, so let me just copy that again before we continue the process with this tableau. So next variable, let's take a look at this row here once again. Again, we need to identify a column that has positive reduced costs because we want to maximize, and the only possible choice is this one here. So that means this will be the variable that we want to take into the basis. Right, now in this case we have 2 positive entries in the column. So we now need to do this ratio computation. And we need to compute the ratio of this divided by that. So here the ratio is 0/1, and here it's 1/1. The smaller of that is the important one. So we have to choose this. Okay? So that means new plus will enter the basis, and S1 is going to leave the basis. Okay, again, we do Gaussian elimination steps. Again, we already have a +1 here, so nothing to do about the first row, apart from changing this entry here. So this now is a mu plus. We need to change this one here. And we do that by simply subtracting, the first row from that second one. And then we also need to take care of the reduced cost. There's a 1 in here. We need to make that a 0 as well. So again, we just subtract the first row from that reduced cost row. Third row is fine. We have a 0 here already. Good. So let's see. For the second row, nothing changes here or here. Here, we get 1 minus minus 1, so that will become a 2. Oops, sorry, a 2. Yeah, different color. Sorry, 2. Let's erase those right away before I forget anything about that. Here we get the desired 0. Here we have a minus 1 minus minus 1, so plus 1, so that's becoming 0. Minus 1 here. And all the rest stays the same. And for the reduced cost row, let's see. Let's erase that as well. Nothing changes here. 0 minus 0, 0 minus 0. So here we get 0 minus minus 1, so that's a plus 1 again. Here we get the desired 0. Here we get a 0. Here we get a minus 1, a 0, and this stays at minus m. Okay, I hope I didn't make a mistake, but we should be at this point now. I think it looks good. We're almost done. I need to take a little overtime today, but I'd just like to complete this computation to show you how to complete that, just in case. But it won't take long, I promise. So copy that. Again, look at the reduced cost row. The only positive entry in that row is this one here. So our next selection is this XR. Right? So we need to get XR into the bases. And again, that's a good sign. Right? That means we can increase XR beyond the value of 0. And we would expect that happens at some point. In this case, we have 2 positive entries. So again, we need to, just a second, we need to compute the ratios here. And those will be this over that. So we have 1 over 2 here, 1 over 1 here. And the lesser of the 2 is this here. So that is going to be our pivot element. Did you detect a mistake? Great. Let me finish the computation and then ask again, please, so I don't have to interrupt this flow here. All right, so this is our pivot element here, the 2. And that means this element S2 is now leaving the basis. What do we have to do here? Well, in this case, it's a little more work because there's a 2 here and we need a 1. Right? So first thing we need to do is subtract this or divide this whole row by 2. And then we need to produce zeros here and also here. And to do this, well, here we have to add 1/2 of that second row. Here we have to subtract 1/2 of that second row. And here again, subtract 1/2 of row 2. All right, so let's start with the new row 2 first. Again, we divide everything by 2. New basis variable is XR. Value is 1 over 2 now. Here we get a 0, here we get a 1, 0, 0, minus 1 over 2, 1 over 2, 1 over 2. Now we can just take this new row and do the additions and subtractions. Maybe that will be a little easier. So first, let's add this new second row to this first row here to get rid of this minus 1. What we get is 1/2, 0. Oh, come on. 0. The 1 and the minus 1 will stay. Here we get 1 minus 1/2, so that's 1/2. And here we get 1/2 and 1/2. For the third row here, we need to subtract the new second row. So what we get is 1/2. The 1 stays. We get a 0 here. The zeros stay. We get a 1/2 here, a minus 1/2 here, and a 1/2 here. And finally, the reduced cost row. Again, we subtract the new second row here. So let's see. This will be minus 1/2 minus, no, sorry, 0. This will stay 0. 0 here. This will be 0, right? 0 and 0. Here we get a, no, not a 0, sorry. We get a minus 1/2. We get a minus 1/2 here, and we get minus m minus 1/2 here. All right. We're subtracting the second row from the last one. This one? No, we're subtracting, so I'm subtracting either the new second row, so this one, from this one, or as I wrote here, 1/2 of the old second row. Yeah? So I need to make sure there's a 0 here. That's the whole objective. All right? I hope I didn't get anything else wrong. At least it seems to look good. So, finally, all of these coefficients are now 0 or negative. No positive reduced cost coefficient anymore. So we're done. And that means we can read of our solution. And we basically have these variables here. Those are the basic variables. So those might not be 0. And that means our solution here is XL is 1 over 2. We just read off the value here. XR is 1 over 2. And nu plus is 1 over 2. And all the remaining variables, x minus, S1, S2, and S3, those are non-basic variables, so those are all 0. Sorry? And Z is 1/2, yeah, right. Yeah, so that's the last thing, Z is 1/2. So that's the value of the objective, right? And of course, that's completely in line with the solution. Remember, the objective was mu plus minus mu minus. Mu plus is 1/2, so that's exactly the value we'd expect. And I hope you will agree that this doesn't come as a complete surprise. So the optimal strategy would be to randomize equally to the left and to the right. And of course, for the goalkeeper, the optimal strategy is the same. The value of the game is thus 1/2. And before you leave, just one more minute, I have a small homework for you to think about that we'll discuss on Thursday. The simplified setup here was we just had two strategies, either aim to the left or aim to the right. Of course, that's not the whole game anymore. but we just make it slightly more complicated by adding a third strategy. Let's say the penalty taker could also aim for the middle. And of course, the goalkeeper will also be able to react, so he can choose to just stay in the middle. Otherwise, the same rules apply. Question, how does that change the optimal strategies? And specifically, how does that change the value of the game? So think about that, and we'll go on with that discussion on Thursday. You're welcome to come forward for your question. I'm sorry I didn't have any more time to discuss that.